Okay. Hello. Let's see. Hi. Okay. I guess. Oh, sorry. So today we have. So yeah, today you can hand up assignment 1. Well, on my e-learning. Let's see. Also, I just wanted to continue reviewing some concepts from group theory and hopefully introduce some examples. Okay. I've been behind with video production. So I apologize for that. Yeah, I hope that I can get back on track with everything. Okay. Before we get started, did anyone want to ask any questions about anything? Okay. Okay. If you have any questions, you can either just, I believe you can unmute yourself and ask, or just type in the chat. That'll be fine. Okay. Oh yeah, one more note. We'll take a break like about every half hour. That's probably what we should do in general, but this break would be so that we could keep on using Zoom. But I guess it would be best to all take that break anyways, so it's not bad. Okay. So when we take a break, I'll shut down the meeting, ask you to sign back on again. Apologies for that. Okay. So let's remind ourselves what a group is. Okay. A group is a set G equipped with a binary operation call it times if you want. And the input into the multiplication is 2 elements of G, and it gives you back an element of G. I wonder if I should zoom in. Okay. Right, so we've seen some examples already, but let me just tell you a few quick ones. You have the integers under addition. Oh yeah. And in my definition, I forgot to tell you what the binary operation satisfies, but let me just tell you what the integers satisfy, and then the group operation will satisfy that. Okay, remember the integers satisfy there exists 0 such that 0 plus n is n plus 0 equals n for all n. 2 satisfies n plus m plus l. That's the same as n plus l. And also we have negatives. For all n, there exists negative n. Such that n plus negative n is negative n plus n equals 0. Yeah, that's what the integers satisfy. And many other things. One key other thing, also it satisfies 4, which we put in a kind of a different category. Okay. So here we have the set is the integers, and our binary operation is just addition. And we have these 3 properties. There is an element that you can add that doesn't do anything. Okay. If you group up addition in different ways, you get the same thing. That's the associative property. And then each integer has a negative corresponding to it. When you add them, you get the identity 0. Okay. And then we have this 4th additional property, which we kind of group separately. N plus m equals m plus n. Okay, so let me now get back to the definition for a group. Well, we're just going to write down these same 3 properties, except whenever we see plus, we'll replace it with the binary operation of our group G. And instead of 0, we'll put 1. Instead of negative n, we'll put n inverse, or sorry, G inverse, whatever. Okay. So let's go do that. So definition of group continued. Okay. So the operation must satisfy 3 things. 1, there exists, I usually call it E, such that G times E is E times G equals G for all G. Okay. Let's see. We need for each G, there exists a G inverse. Okay. And then the third property is called associativity for all, let's say GH, K in G. GHK is GHK. Okay. And then if we have if we have a set with a binary operation and these three properties are satisfied, then we have a group. Okay. That is what a group, that's our abstract definition of a group. Okay, and as an additional note, if GH equals HG for all H and G, then G is called an abelian group. Okay, so we're off to a good start. The integers, that's an example of a group. Okay, so to tell you a group, I have to tell you the elements of the group, and I also have to tell you how to multiply them. And one way to do that is to give you a multiplication table or to find multiplication in some other way. Okay, so let me try and give you an example of a group, of giving a definition of a group using a multiplication table. Just a simple one. Okay, we'll do V is going to be E, A, B, C. And multiplication let's see. It's going to be like this. Okay. Now I want to fill in this table so that all my group laws are satisfied. One of the first group law says that E times everything, like E times anything should just be the thing. So it means like E times E should be E, A times E should just be A, and so on. Okay. Let's see, I want for each element of the group to have an inverse. I'm going to choose the inverse of each element to be itself. So I want A times A to be the identity, B times B to be the identity, and C times C to be the identity. Okay. Okay, now we can try and fill out the remaining 6 spots. You know, so we have to figure out what is A times B. Okay, so let's use like some scratch paper. We want to figure out what is A times B. Like, what could it possibly be in order to get like to satisfy all the 3 properties? It could be the identity. Okay, but if A times B is the identity is also A times A. And then if we had A times B equals A times A, then we could kind of like cancel off an A to get B equals A. Okay, so we don't want B equals A. We want these to be 4 distinct things. So we can't have the identity A times B equals the identity. We also can't have AB equals A. Since you cancel off the A, you get B equals the identity. That would be bad. Okay. Similarly, you can't have AB equals B. So you pretty much have to choose that A times B equals C. And you also have to choose that B times A equals C. And A times C has to be B. C times B has to be A. Okay. So it turns out once we specify that we have 4 elements to our group, once we specify that E has to be the identity, and once we specify that once we've written down the that the inverse of A is A, the inverse of B is B, and the inverse of C is C, like the rest of it is already predetermined what it has to be. Okay. Maybe now's a good time to remind you that we have like, due to the existence of inverses, we have like a cancellation law, which is what we use when you're trying to figure out this multiplication table. Okay. Oh yeah, and I should mention now, like we did not check that the associative law holds. You know, we would need to check that X, Y, Z is equal to X times YZ. Because that would take a long time. Well, not so long, but it is boring. Okay, but it turns out to be true. Maybe there's like a tricky way that you can check it, but we're not going to do that. Okay, anyways, yeah, so this is a group. But let me just tell you about the cancellation law. Okay. Okay. So the equation, gx equals h, or I'll say the equations, and xg equals h have unique solutions. X and G. Okay. That's one part of the proposition. Is basically telling, I mean, and here the idea is, you know, we just multiply on the left by G inverse. Okay, so because I guess we're getting warmed up, let's just try and prove this proposition. Okay, so let's suppose G and H are in a group, and let's solve Gx equals H. Okay, so first there exists G inverse. Such that G inverse G equals the identity. Now take this equation and multiply by G inverse on the left. Okay. Now, by the associative law, we can rearrange these brackets. So you can rearrange it like G inverse Gx. That's associative law, or associativity. Okay, but the law for G inverse says that G inverse G is the identity, right? So this is really the identity times X, and that's equal to G inverse H. Okay, that's like the inverse law, I guess. And now E times X, that's just X. Identity law, if you want. Okay, so it tells us that if Gx equals H, then X equals G inverse H. So that means that if the solution exists, it's unique. Okay, now we just need to check that this is a solution, which the way we constructed it, it definitely is. So notice G inverse H is just G inverse H, which is just EH, which is H, which satisfies Gx equals H. Okay. So we've shown that the equation Gx equals H has a unique solution. And for the equation Xg equals H, it's similar, but you just multiply on the right by G inverse. So you get Xg G inverse equals Hg inverse, and then that implies that X equals Hg inverse. Okay, so I won't go through the details again. It's the same except for the first part where you multiply on the right instead of on the left. Okay, so this equation always has a unique solution. So that gives us several useful properties. So now it tells us, so this tells us that G inverse is unique, meaning that for each G, there's one and only one inverse. We can't have more than one inverse. Okay. This also tells us, it also tells us that the identity is unique. Meaning there's a unique identity element. It tells us that, the cancellation law. If GH equals GH prime, then H equals H prime, and if HG equals H prime G, then H equals H prime. Okay, all of these things can be deduced from the last property. Okay, so we have the cancellation law, inverses are unique, all that nice stuff. Okay. So now we can really, so that tells us why. So so this is why when trying to find the result of AB, like trying to make up a group law for this set E, ABC, we couldn't have AB equals A, for example, since AB equals A, well, that's just AE, A times the identity. Then that would imply, if we had a group with AB equals A, it would imply that B equals the identity by cancellation. Okay. So all these different inverses and stuff like that force us to take AB equals C in that example. Okay. We also have a notion of subgroups. Okay. So let G be a group. And let H be a non-empty subset of G. Okay. And H is called a subgroup. Okay. Well, what needs to happen? H needs to be a group, but since it's a subset of G, it kind of inherits the multiplication of G. Okay, so if you take the multiplications of G and apply it to H and you get a group 2, then you call H a subgroup. Okay, so H is called a subgroup if 1, H is closed under multiplication. That just means that GH, oh yeah, it means that for all elements of H, G times H is in H. Okay, and 2, H is a group under the group law, I guess under the multiplication of G. Okay. Okay, as an example, you have a theorem. Let H be a subgroup of the integers then there exists an integer n such that H is just the multiples of n. Like that. Okay, and furthermore, I guess the other part of the theorem is that these things like this are all subgroups. So if we call this NZ, furthermore, NZ contained in Z is a subgroup of Z for all n. Okay. So if in terms of subgroups, if we want to study the integers, we know a lot about the subgroups of the integers. Okay. What would be the proof? Well, I guess one of them I want to be an exercise and the other one we'll go through. So you have to prove two things. You have to prove if H is a subgroup, then it has to be the multiples of some given integer. So let's prove that, and then I'll leave it as an exercise for you to prove that the multiples of n are a subgroup of Z. Okay. Prove NZ is a subgroup of Z. And the steps to this exercise would be step 1, 0, that's just n times 0, which is in nz. So the multiples of n are non-empty. Step 2, if let's say a and b are in nz, then you have to check that a minus b is also in nz. So you have to check this. And the trick for that is you have to write a as a multiple of n, b as a multiple of n, and then factor out the n in a minus b. Okay, and then once you do that, then you apply the subgroup test, which tells you a group that is non-empty, it's closed under, in this case, subtraction. It has to be a subgroup. Okay, so now we would apply subgroup test, which says H is a subgroup if 1, H is non-empty, 2, for all G and H in H, GH inverse is in H. Or you can replace that by two properties. You can check that for all G and H, GH is in H and H inverse is in H. Yep. Okay. So what I really wanted to go through was the proof that H is the set of all multiples of some given integer. So let's suppose H is a subgroup of the integers. Okay. And let S to be the elements of H such that n is bigger than 0. Okay. Now, if S is empty, then H has no positive elements. And we claim that H is just the single element 0, like the trivial subgroup. Okay, let's prove this claim. If S is empty, H has no positive elements. So suppose M is in H and M is not equal to 0. Then M is not in S, since S is the empty set. So M has to be less than 0. Then negative M is in H. Since H is a subgroup, it's closed under taking inverses. Okay. And negative M is positive. So negative M is actually in S, and this is a contradiction. So if H has no positive elements, then its only element is 0. Okay, and now if S is non-empty, then S has a least element. Okay, this is by the well ordering principle. or induction. But we'll use the while ordering principle. Okay, so we're gonna take like a 5-minute break. Okay, so I'm just ending this meeting and I'm just gonna restart it right away. Okay, and I won't start for another 5 minutes, so you don't need to jump back in immediately, but if you want to, you can. Okay, so let's do that.